record? Because so my other class did not change. Like I said, am I recording? And they went, yes, you're recording. It says right here. And I wasn't recording. So that's annoying. So I don't know if I can share the screen and then start record. I might have to start record before I share the screen. So I'm in the Unit 1 worksheet for intermediate. And I want to go over here. How many of you have done this? This part of it.
What, you mean integration or differentiation?
Well, the differentiation.
Oh.
I have.
So if I went through here, we could go through the answers.
I did parts of them, but not all of them.
So what is this? What is this implying here?
Which one are you pointing at?
The first one, dc dx.
You're differentiating a constant with respect to x.
So how does a constant change with respect to x? With my
It does not.
We're going to start thinking, zonal location, and the answer is it's not. So the first one's 0. Now dx is what? How does x change with x?
1.
The answer is 1, right? What about dx squared?
2x.
It's going to be 2x. Now, I want you to look in here and think this, because I want to show you, I just want to make sure that we understand what I'm about to say. So let me get my pen out. Over here, dx squared dx is going to be 2x. But if you ever saw in here dx squared, you would say that's 2x dx. So what you're saying is that the derivative of this thing, of whatever this function is, squared, is 2 times the function times the derivative of the function. So let's say that I did, and I just want you to look at it this way, dx to the 6th. We can say that that is dx squared to the 3rd power. Do you agree that that's x squared to the 3rd power is 6, x to the 6th?
Yes.
Yep.
So we'd say the derivative of this function cubed is 3, that function squared. But, d times, times the derivative of that function. And we're saying that this function here is x squared. So it's going to be really 3x to the 4, hold on. It's going to be 3x to the 4th, because that's this x squared function squared, times the derivative of x squared, which is 2x, which makes 6x to the 5th, times the derivative of whatever x is. So I just want you to see how I can kind of break things apart into simpler functions in there, and just keep this in mind. So I'm always, anytime I'm saying whatever, and I know we use the letter x a lot, so I say whatever is in the circle, I'm taking the derivative of what's in the circle. That's the way that you need to think about it. So dx to the 3rd would be 3x squared. If I brought the dx on that side, I could go the derivative of x cubed is 3x squared plus the derivative of whatever that is. So if you, rather than thinking that as x being specifically x, think of that's the derivative of whatever that thing is, whatever that thing in a circle is. And this will help you in integration when we start to go into integration. Okay, let's continue on with this one. The derivative of any constant times x is just you bring the x out, or the a out in front, times 1. So this comes outside, Over here, it comes outside, and then the derivative of x squared, which is 2ax. What's the derivative of cosine of x?
Hold on,
Negative
sorry, what was
sign.
the?
Is it the sine of x, or is it the negative sine of
It's
x?
the negative sign.
Negative sign.
And the reason is because when I look at my function of cosine of x, at the top, it's 0. And then the first set of values is negative. Okay. The slope is negative. Okay, and then the derivative of sine of x is cosine of x. Now I know, see, here's something. When I first got hired at COD, they said, you can't do it, you can't have a meteorologist do this. You can't hire a full-time meteorology person. Because no other college in the country had a full-time meteorologist at a community college. And they took a chance on me. And I said, okay, hold on. I'll do this. And they said, well, you might have to teach like the intro to earth sciences. So I had to take geology because I didn't have geology. So I took the first 3 semesters of geology. And I did really well until I got to the third one, which was the history, like the Devonian age and the Cambrian, and all these other ages. And the only way to know that is you had to memorize when they were. There was no way to figure stuff out. And I'm not very good at memorizing stuff. Like, when I direct my choir, I can never say the name of the title of the song because I don't remember what it exactly is. And it's usually embarrassing, and I use it for humor. But in science, you can't afford that. So in math, a lot of times they say memorize these derivatives. Well, I was never good at memorizing. So I had to figure out a way to view, especially a couple of these, how to remember how to do that. So just keep in mind that a lot of times I tell you secrets to figure out what they would be so that you don't have to memorize it. But if you struggle, memorize them. Okay, now this.
What was the answer to 2ax over dx again? That's the only one I didn't really get there.
Which one?
2ax over dx.
That's not in here.
Is it an A?
The answer is 2ax. Because the a
Okay.
comes from, and then the derivative of x squared is 2x.
Okay, so it just goes, okay.
Now this one, because you have this, you can break it down into the derivative of ax dx plus the derivative of bx squared dx. So this becomes a plus 2bx.
Pardon me.
Okay? Now what's the derivative of the natural log of x?
1 over x.
What's the derivative of x to the minus first?
Minus 1 over x squared.
Minus 1, yeah, times x to the minus 2, right?
All right. Same
Mhm.
thing.
Because you lower this by 1 and bring it in front, negative 1. So what's the derivative of e to the x?
E to the x.
That's an easy one, right?
Right.
Derivative of e to the 2x. Now, again, I want you to think of this as what's the derivative inside that circle? Is 2. So I take e to the x is really the derivative of what this is in front, which is 2e to the 2x. And then this one is kind of odd. Remember, what is this going to be? Derivative of a times b is just a times the derivative of b plus b times the derivative of a.
Oh, okay.
Right? What is that called? What rule is this?
Product rule?
Product rule. Okay. So are we good with all those? So there's your derivatives. I'll give you derivatives on a test that should be pretty easy because these are the key ones. I'm not going to give you any funky sine x, cosine squared x type stuff. This is the ones that we need to do this section of this this entire class.
Could you go over the derivative of e to the 2x again?
Okay, so
Yeah.
let's go to this. Let me go here. So again, what I need you to think of is anytime I have the derivative of e to something. So let's call it this, Bruce. This is the derivative of e to something. Is always e to something times the derivative of something. Maybe that's a better way to think about it. The derivative of e to something is always e to something times the derivative of that something. So what is the derivative of something in this case? You're taking the derivative of 2x times e to 2x. Well, what's the derivative of 2x? It's just going to be 2 e to the 2x times the derivative of x. Because I could have, what I could have done, Bruce, is I could have done this, 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 and then I get rid of that. They cancel out. So it's just e to the 2x. So again, I think the problem you guys run into is you think,
I see.
oh, it's x. It's the derivative of x. What does that mean? It's the derivative of something. If you put in other words other than x, then you don't think mathematically, and you go, oh, I see what you're doing. Does that make some more sense, Bruce?
I think so. I'll just go over the notes later.
Okay. Everybody else good on that? So let's go.
Yeah, I think that makes a bit more sense now. I see what I was doing wrong.
So let's look at integration. And this is basically, this is harder, but it's thinking, what I need you to think of is this. So I'm going to watch this. For this one here, I'm thinking the answer is something. So the answer is, what's the answer to integration of cosine x dx? Something. Now, if you write this on a test, I'm going to have to cut it off. But do you understand that integration is really the opposite, is the inverse function of the derivative. So if I take the derivative of both sides, what ends up happening is this goes away. So what I'm basically asking is, cosine of x dx is the derivative of something. So the derivative of what equals cosine of x?
Negative sign.
Right? No.
It's sine.
So that something must be sine
Oh,
x.
yeah.
Because the derivative of sine x is cosine x dx times the derivative of x.
Plus c.
Well, I'll have it in a second. Okay, does that make sense to you? So the integration of cosine of x is sine of x. But I want to look over here for a second. So I'm going to blank this out. And I'm going to go, wait a second. I said the derivative of an integration of something is just the derivative of something. Else. Make sense? And in this case, I said, well, the integration of cosine of x dx is equal to sine of x. Do you agree? So what is something? Cosine of x dx. What is something else? Sine of x. But do you agree that something else could have been sine of x plus, I don't know, 4? Because if I take the derivative of both sides, that goes away, right? And I take the derivative of this side. What's the derivative of sine x? Cosine of x dx. But what's the derivative of 4?
0.
Isn't it 0? The derivative of a constant is just 0. So I guess, in other words, I could have had something else there. So your concept is, when I have the derivative of a function of x, it's going to always be some answer plus a constant. You have to always add plus a constant. Now, 95% of the time in this class, it's not going to matter if you, it's not going to matter if you forgot that. But there's a few times where that plus a constant matters. And we'll explain why it matters, because it tells us some information. Okay, so you need to go through that part of the lecture again if you're struggling through this.
So you said integration is the opposite of derivatives, or?
Inverse. Yeah, it's like the inverse.
Think
Inverse.
anti-derivative.
It's called the antiderivative. Thank you, Jim. So in this case, let's look at this guy over here. What would the answer be? If I took the derivative of what is the sine of x?
Minus cosine x plus c.
Well, it's going to be cosine of x plus a constant. Remember the plus a constant. If I had taken the derivative of this side, you understand the constant goes away. But what's the derivative of negative cosine of x? The negative goes outside. What's the derivative of cosine of x?
Negative sign.
Negative sine x. The negatives go away. So a lot of times you have to watch out for that negative sign. You will find in math, negative signs cause you problems. The difference between me getting a B plus in a class and an A minus was I screwed up a negative sign.
Negative signs, man.
Okay? Now what about this? Dx over x, what's the derivative of this? This is so important. Like, the derivative of what is dx over x?
Natural log of x.
Natural log of x.
The absolute value of x.
I won't worry about this.
Cheater.
I'm not gonna deal with that in this class. I don't want to go into this. The idea being is, can I take x to be negative? So the reality is, if I were to, remember, if I had a function and I tried to integrate that function 1 over x, where you get this, right? You're taking the area underneath the curve. Do you understand? Remember, integration is the area underneath the curve. Do you guys remember me saying that?
Mm-hmm.
Yeah.
Is there any curve over to the left? Well,
No.
there is a 1 over x, but I can't take the natural log of negative x's. Although I can, but. So we're not going to worry about that, okay? So this is the natural log of x plus a constant. Now, this is why I did that whole thing with the derivative. See, if I went over here, I took the derivative of the natural log of x. With respect to x, it equals 1 over x, right? But if I bring this to this side, I get dx times that, which is dx over x. And so this side doesn't have the d, you know, this, you don't have the dx over there. Now, just so you know, this one is the most important of all the integrations for this class, because we're going to see it a bunch of times. We're going to integrate from whatever to whatever. Now, one last thing I'm going to do in here with the white screen. When I take a function like this, we said that the answer is the natural log of x plus a constant. What are these things called? Actually, let me do this. Color helps. What are these things called that are supposed to go there?
Limits.
Yeah, those are called the limits
They define the domain.
integration. I'm integrating this function from here to here. And when I actually have a limit, let's say a to b, I would put a to b over here like this. Remember the little limit sign, the interval sign? And what that's going to become is the natural log of b plus a constant minus the natural log of a plus a constant. When I don't have limits written there, like on the worksheet, that's called an indefinite integral. There's a name for that. They call it an indefinite integral. In other words, I'm looking for the function. I'm not looking to actually solve anything. I don't know what it is. It's indefinite. Guess what do you call it when I have the limits of integration?
A
Definite.
definite function.
A definite integral. When I do a definite integral, do you understand that the plus c minus a plus c, they go away? So that if there were a constant, it won't matter when I actually solve the problem. That constant won't have anything to do with it because there is nothing else to deal with. So do you understand that the answer to this is then going to be the natural log of b minus the natural log of a? Now, no one say it, but what should I do when I get here? Don't say it. Write it out on your own and tell me what I'm looking for. The natural log of b minus the natural log of a. Okay, how many of you wrote something down? Okay, well, Mike, how about you? Did you write something down there?
Yeah, pretty sure it's the wrong answer though.
What did you write down?
1 over b minus 1 over a.
No? James, what did you write down?
Change of b.
No. These are natural log functions. Remember the rules of logs. Jacob? Jacob, are you there?
Isn't it a natural log? No. Yeah. Natural log of b over a.
Ding, ding, ding.
Remember the rule? That's just, these tricks are going to be super important in what we're doing. Natural log of b over a. If this had been a plus sign, remember what plus would have been?
Product rule would follow, right?
That would have been times a.
No.
Remember, the way that we think about it is that this becomes a plus and this becomes negative. That's why you get this. So those are just some tricks that you need to remember how to do.
How would that have been a plus A?
If it had been natural, it wouldn't have been, and not in this problem. I'm just saying, if I took two natural logs and added them together, you would have done that.
Just wondering with limits like A and B, how do you get A plus B?
Right? No, it's not. I'm just reminding you of the product rule. Okay. So that's these two we got. This one we got. Okay. What's the integration of x of dx?
X plus C.
X plus a constant. Do you agree that if I took the derivative dx is dx plus c? Now, what about this one?
X squared over 2 plus C.
It's going to be x dx. I want to take the derivative of something is going to be equal to the derivative of something else. So I get rid of this 2, and I'm like, x dx is the derivative of what? Isn't it x? Like, if I took the derivative of x squared, what do I get? I get
2x.
2x dx. But over here, I have x, and over here I have 2x. So what does that something have to be?
Divided by 2.
It has to be divisible by 2, because if that were in there, then those things would go away. That's the hardest part of integration, what I've just done. Because you have to find that missing something.
How does the DX creep back in there?
Because if I divided both sides by this, it would go away. And then x equals x. Remember, the derivative of something is always the derivative of that something plus, like the derivative of x squared is always the 2x times the derivative of x dx. Because I'm doing it, so watch this, Bruce. Let me just take it here. Is equal to 2x times the derivative of x. If I put it over here, that's the way that we often think. That's a question. How does x squared change with respect to x? It's 2x. But since I'm just leaving it without the how does x squared, I'm sorry. Let me rephrase that. What's the derivative of x squared, right? Not with respect to anything. It's just always going to be 2x dx. So just remember that I can always bring that over if I want to. I can bring it over.
So the answer is dx squared over x.
So the answer for this one is x squared over x. Over 2.
2.
Over 2. Good. Wrap. Plus a constant. So let's generalize this. A times x. What can I do with the a?
Pull it out.
The answer goes front. So I already know that x dx is going to be x squared over 2 times a plus a constant. And you just got to get used to always saying plus a constant. Okay, so those are your integrations. So I've helped you with that part of the worksheet. But now let's take a look at this. So, what about this?
You can replace, since P is equal to F over V, you can rewrite the equation so it's the integral of F over V dV.
Nope.
No?
I mean, I looked it up, but
Okay, well, here's what you need to be thinking over here. That you have pressure. You're saying the derivative. If I took the derivative of both sides equals the derivative of what? Equals P times the derivative of volume.
Oh,
So what I'm saying is that this is a function times how volume changes. This is a function times how volume changes. But do you agree that pressure is a function of volume? Do you understand when I say pressure is a function of volume? A better way to say that? Do you understand that? What's a better way to say pressure is a function of volume? Anyone? Bueller?
It's on the tip of my tongue. I just, ugh.
Ended upon.
That's the way you should say it. The pressure depends upon the volume, right? They're related to each other. So we use mathematical terms like it's a function of, but what we're really saying it depends upon. So what I'm saying is, in this case, when I see pressure, and this is the hard part, guys. This is your brain trying to figure out what I mean. This is a value. This is a value.
scalar is what you're.
This is saying volume is changing. Well, what is the pressure if the volume's changing? Doesn't the pressure always change? If the volume's changing, isn't that changing the pressure?
if you're looking at it in terms of like ideal gas,
Okay,
yes.
if I took an ideal gas, and we're going to be getting into this, but I'm going to look at this, P equals V R T times N.
nRT.
Okay, and we'll explain the different ideal gas laws coming up because we need to get to this. But you've probably seen this. Another way that you could look at it, and I actually prefer it this way, would be pressure times volume is mass times RT. Because if I put pressure and I bring volume to the other side, I get mass over volume times RT, which equals pressure equals rho RT, which is the way that in my classes, and you take in my classes, that's how I teach the ideal gas law. Pressure equals density times R times T. But I want you to think of it as this way for now. And what I can do is I'm going to say, I'm going to integrate pressure times the change in the volume. But do you agree that pressure is mass over volume times R times T times the derivative of volume? Okay? Do you guys follow what I did here?
Yes.
I want you to imagine that I've got a box of air. Okay? It's a Vegas box. So what do I know about the mass?
Not changing.
So I can bring it out front. What do you know about R?
It's
Constant.
constant.
Times T dV over V.
Why can't you bring T out?
Why? Well, the answer is, under what conditions can I bring it out?
If T is constant.
If the temperature is constant, I can bring it out, okay? So let's say if T is constant, then what do we got? Then we get equals mass times R times T times the integral of dV dV. Can I integrate this function?
Yes.
Yes.
What does it equal?
Natural log of V.
Plus,
C.
It's a constant.
Integration constant.
It's if T is constant.
what did you say, James?
That's if temperature is constant.
Right. Because if temperature is not constant, do I know this function that I can integrate? Like temperature, it's some changing thing, and the volume, it's some changing V. Oh, I don't know what that is. So I don't know how to integrate that. I don't know the function. I don't know what it is. But if temperature is constant, I can. And then it's an easy function. It's just the natural log. So what I'm saying is, if I keep this box constant temperature, and I change its volume from here, that's not what I want. Do you agree that this is volume 1 and this is volume 2? So what I could say is I could have gone, and I'm going to put it in a different color just so you know I'm doing something different, from volume 1 to volume 2, and then I put volume 1 to volume 2, volume 1 to volume 2, volume 1 to volume 2. In this case, I don't need is a constant. I'm going from volume 1 to volume 2, which means the answer is the mass times R times T times the natural log of V2 over V1 is this. You guys follow me?
Believe so.
So I just made it, instead of being an indefinite integral, I'm giving you from what to what. And remember, I am looking at this box. I'm saying the volume is changing. So do you agree that's a changing volume? Now, this air is expanding. Do you agree with that? And what would that cause if I said a gas expands?
Temperature is changing.
The temperature is changing. But you know, I said the temperature can't change. So what do you call it when I have a temperature that doesn't change? What's the word that means temperature changes?
Isothermic.
Isothermal.
Isothermal.
And I don't know why it's AL versus IC. It's just different. Isothermal. 30-some years of teaching, and I don't know the difference between IC and L. I just know that that's the word. That's an isothermal process. What if it wasn't isothermal? What if I just let the box expand? Then the temperature is changing, right?
Yes.
But if I expanded the box because the temperature was changing, what could I say? What if I said that the pressure was constant? I could have said pressure is constant. Then I wouldn't have to do any of this stuff. I would just put P dV. That's easy. I wouldn't have to go through all this. So just be aware of this. So these things you're going to see numerous times. Let's go back to this. And I said graph y equals x from x to 1. And this becomes pretty straightforward. Y, x, here to here, 0 to 1. I'm looking at the area underneath the curve. I'm going to integrate from 0 to 1, x dx. The integration of x dx is x squared over 2 from 0 to 1, which is going to be 1 squared over 2 minus 0 squared over 2. I get rid of that. I get 1/2. Okay, that's a definite integral from 0 to 1. But we already know that those are pretty straightforward integrals. So over here, are you writing that down? You want to finish up writing? And let me know when you're done.
Equals 1/2.
Yep.
Now that thing that you wrote down for the derivative of PdV, is that the answer you were kind of looking for, or are we going back to that?
Well, the idea, no. The idea is that question that I'm asking in the worksheet is really, you can't answer that unless you know more information, right? Because you don't know how pressure changes with volume. If I said the pressure were constant, it's easy because I figured outside. But if the volume, if the pressure is changing and the volume's changing, then you need to know something else. Then I gave you another piece of information that says, well, it's isothermal. But what if it's not isothermal? What if I lift a box of air and it expands? Do you agree that the volume, the pressure, and the temperature are all changing?
Yep.
Can't do that, okay? But so there is no answer unless you get more information. Right. In my brain, I've determined a long time ago that when I struggled through the science, because I knew my math, I knew how to do this stuff. I was good enough at doing it. When I came to science, I'm like, I don't understand. What am I not doing, or why can't I do this? You have to understand when you can't integrate and when you can. So if I said it's isothermal, then you substitute a couple things and you do it. If I said the pressure's constant, it's easy to integrate and bring it up. But if you don't have those two, I can't do it. Now remember that this is y over x in this case. Or you could have said this is the function of x, right, versus x. And we said y equals x. So that's what we've been doing. Remember how we found out if this is 1? And this is 0? We said it's the area. Well, what is it the area of? It's the area of a bunch of these, what? These rectangles. How big are the rectangles? How wide are they?
Dx.
They're infinitely small, dx, wide. How tall are they?
Y tall.
They're y tall. They're f or f of x tall. So what am I actually doing is I'm summing up f of x dx. That's where the dx comes from. It's this rectangle. So if I said to you P dv, if I could graph this and do the same thing. But this time, what is this axis? I'm changing the velocity, so this is the the volume, not the velocity. This is the pressure. Now, if I were to make the volume a lot smaller, what do you think the pressure is going to do? Take a box there and make it really small. Won't that make it really high pressure? Now, I don't know the relationship. Do I know how to graph this? Answer, no, I don't. But let's just say that I did something. It's something like this. And we'll see why it's going to be a certain way. But it's some function. The smaller the volume, you agree this is saying the smaller the volume, the higher the pressure.
Yes.
So I don't know what this really looks like. I don't know the function, but I know that that's kind of makes sense unless I did something different. Like, could I make here, let me ask you this. Could I make a smaller volume less pressure?
Technically, I think yes.
What would you have to do? What would you have to do?
You'd have to change the, I believe the density and the temperature.
Well, volume is the density, but
I'm sorry.
yeah, you change the temperature, right? If PV equals mRT, do you understand that pressure goes up as volume goes down? But what if the temperature went really far down? Couldn't I make all of them less?
Yes.
So if I could make the temperature really, really cold. Now you understand, we talk about adiabatic processes, well that's different. But if I'm pouring heat out of it, if I'm making it super cold, I could make everything down. So again, I don't know what this graph looks like, at least as of now. But if this is at least one example where it makes sense. So what I'm really looking for is if I change the volume from there to there. Big volume to smaller volume. That's going this way, isn't it? Pressure goes up. And what would this term integrated be? Well, I would be summing up rectangles. How big are those rectangles? How wide is this rectangle?
dv.
dv, because they're dv wide. And what's the value of the y-axis?
E.
That's what I said. I'm integrating P times dV. What is this?
The name?
Yes.
Is it called the integrand?
No. What is
Oh.
pressure times the change in the volume?
Formula for density?
Okay, want to see something so freaking cool? I'm going to start again. I'm going to start with this. I'm going to say, I want to know what this means. What's pressure?
Force
Force over
over an
volume.
area.
Oh, area.
What's volume? Isn't, if I took a box of air, isn't it just whatever that area faces down here times dz? But if that area is a constant, what can I do with this derivative?
Pull the area out, and then it cancels with area down there.
And I have force times what?
It's work.
This is work. Woo! This is so cool. You understand that's work?
Work.
All right, I'm gonna go get a cup of coffee. Please hold. Want to hear something really funny?
Sure.
You're not there yet. Let's wait till everyone's done.
Man, it's nice to see some rain again.
Oh, yeah, we've got a good amount of rain. Oh, it feels good to get my grass watered. There's some serious cold air coming in out of Canada, that's for sure.
Oh, yeah, I saw that. Oh, man. Fall is approaching.
Is everybody back yet? You miss your chicken?
It's two of us.
No, I mean, it was always so funny. Those chicken and a biscuit stuff in the morning is absolutely my favorite, and I just love those.
I know, I missed it so much. It was like such a nice early morning snack to eat.
I know.
The freaking milkshake, too.
Okay, who are we missing? We're missing Bruce and Nick. Jacob, you there? Jacob, where's your camera, dude?
I'm here.
Where's your camera?
I'm eating breakfast. I figured no one wants to watch me eat breakfast.
Well, eat quicker and start using your camera. So I got to tell you something that's just really funny. I just got so I have a podcast app, and it tells me when there's a new podcast. You want to hear the latest podcast title that I looked at the second I said we finished? It says,
Oh.
The Intrinsic Value of Work. I'm like, that is an appropriate podcast. Okay, let's see what's going on.
I hope he's materializing from the Aurora Borealis.
It's like Field of Dreams or something. Okay, so we can go ahead and erase all that stuff. And let's just see where we are.
Pardon me.
Actually, I want to erase all this. Okay, so now we okay, so we got that stuff with the integration. So hopefully this makes some sense to you. If not, go back and check it out. And then there's just some other stuff that you need to look up and take a look at. Then we start going into scale height. So now these problems that I want you to do, did you do problem 1.119?
Yes.
Okay. So this is the sheet that I want you to turn in before class on Thursday. Because really, we should be able to do all of this stuff. This is an old sounding, just to give you an idea of how old I am and how long I've been teaching. This was a Peoria when they used to have the radio sign. But now it's in Lincoln, but they used to be in Peoria. 23rd of September, 1991. And all I'm asking you to do is to calculate the log of the pressure. And you can use millibars, the natural log of the pressure. And then you plot them out. And then you determine what the scale height is, okay?
So you just take natural log of pressure and then plot?
Yes. And when you, remember, the scale height is where the pressure drops by a factor of how much?
E.
Okay, so if I did something like this, I said that the scale height is when the pressure from the surface drops by a factor of E. What if I took the natural log of this? I get the natural log of the pressure minus the natural log of E. But what's the natural log of E? They're inverse functions. I get minus 1. Does that make sense?
Yes.
So if I want to know that, all I'm saying is the only thing I really need to do, what's the natural log of 994?
6.9.
So if you did this, it's 6.9. And then I'm going to look at a graph. And the nice thing about a graph is a natural log. If pressure decreases exponentially, then the natural log should decrease linearly. So I'm going to look for when it drops to 5.9. And then I look at a graph, height versus the natural log of P, and I'm like, there's where I'm going to find it, at that intersection point. So I'm not going to let you take a look at that. I'm just saying that's what goes on.
So the scale height is where it drops down by 1 from the starting point?
Yep. If I do natural log. If I do regular pressure, it's by a factor of E. Same thing. Natural logs make exponential curves linear. Okay? Therefore, this worksheet you should be able to get done by Thursday. This other stuff is just doing your work, right? We've already dealt with a lot of this hard stuff, and then we go through the rest of this.
Did any of you guys have trouble putting the numbers in the derivative and the integral boxes?
Which one are you talking about in here?
Just putting the answers in. I couldn't, for some reason or another, it wouldn't let me do it.
I had to put the answers in a separate space. I couldn't put it in the box.
Yeah, same here.
Oh, well, that's okay.
Yeah, it's easy for me. It's easy for the derivatives, but it's harder for me for integration.
Do you have a
I can
little
rewrite the derivatives easily, but the integration is, I don't know how to rewrite.
pen like this? Like I've got? Where you can draw on this?
That's what I've been doing, but
If you have, you know, this funny thing, it's called XP Pen. It has a little pad that you,
XPPEN?
XPPEN, yeah. It's got this little pad, and that's what I'm writing on, and it hooks up the USB port, and then I just use this little pen, and they've got replacements and stuff. It is, and it's cheap. It's like, I think it's under 40 bucks. But that allows you to write into the documents pretty straightforwardly.
how do you know where you're writing?
So when I'm writing like this, it shows me the mouse. It shows me this little cursor, and there's a little tablet within this area. So,
Oh, okay.
so that I can just go there, and this is where I'm writing. All
Okay.
here.
Which one do you use, Nick?
What I do is I got a Samsung tablet for about 300. I figured it was going to be good for
Okay.
notes down the road, and it comes with a stylus, so that's
So-
more expensive.
If you have a tablet or something and it comes with the stylus, that's great. This is a really cheap way of doing this, and I found that it's it's really pretty good. It's not as good as writing on the tablet because you're actually writing where it's putting the ink, and now you just have to figure out where this is. So sometimes I get a little bit messier because I have to think about the paper is where the letters would be. But I've gotten used to it. BV equals nRT, right? That's pretty neat, isn't it? So, okay, so I'm going to close out of that. Not going to save any of that. That would be silly to save. And we need to start thinking about kinetic theory. So, how many of you are finished with that worksheet?
Mostly, it was the
Yeah.
integration stuff that was giving me the hard part there. But I think I.
All right, then I'm going to give you another assignment, and I want you to watch episode 44 of the Mechanical Universe. And then I will eventually have you do episode 45, but not for a while. I know these are old and they're outdated in terms of some things, and they're kind of slow and weird, but man, I'm telling you, they're so good. So go ahead and do that. So now, I want you to get out your textbook, and we're going to do some stuff on kinetic theory. So now we are finished with chapter 1. We are not going to do chapter 2. We're going to go to chapter 3. And now we have to figure out a couple of other things. So let's do it this way today. I'm going to use Epic Pen. Epic Pen.
Epic Pen.
And what's inside this box? Molecules. And what are the molecules doing?
Work.
Moleculing.
Molecules got a molecule, right? They're moving around, and we say they're randomly. When do they stop moving randomly?
At T equals 0, absolute 0.
0 Kelvin.
Well, no, I'm sorry. Let me rephrase my question, because I know why you answered what you just did. What makes a molecule, like how is a molecule actually moving? We say randomly, and that's kind of true, but a specific molecule is moving what? How is a specific molecule moving? What'd you say?
Somewhat chaotically, but within a pattern
No,
that we just can't understand.
A molecule, the molecules in general look like they're random, which is kind of true. But a specific molecule is not random. How is it moving?
Kinetically?
What'd you say?
Kinetically?
No,
You talking Brownian motion?
no. Each molecule moves Newtonianly.
Oh,
It moves how? In a straight line. That molecule is moving in a straight line at a constant speed, right? What would make it move faster? If I gave that molecule energy, it would move faster. But if I had only one molecule in this box, do you understand that the molecule would be moving in a straight line at a constant speed until when? Until it hits the wall of the box. At which point, what would it do?
Bounce
Move in the
off and
opposite
go another direction.
Bounce off and go in another direction. Now, if I'm assuming it's moving perpendicular to one of the face planes, as I've tried to illustrate in here, the molecule is actually going to do this. You know what? I'm going to do this better because like a picture on a wall, I can't stand it if the pictures are not straight. The molecule is going to do what? It's going to move this way until it hits the wall, at which point, how will its velocity change? If it hits directly perpendicular, it will come back at an equal magnitude, different direction. So if this velocity is 30 meters per second, what would this velocity be?
30 meters per second.
But it would be in another direction, so it would be negative.
-30.
So we really say that the force we have is really the change in the momentum with respect to time. That is what the force not only is equal to, that is what it's defined as in the Newtonian sense. In this case, that force is going to be equal to the mass of the molecule times dV dt. And what's dV equal to in this case?
30.
No.
No.
Anybody? What's dV in this case, in this example?
60.
60 meters per second.
How did you get 60?
Well, this is positive 30. This is negative 30. What's the difference?
Oh, okay, I see.
30 minus 30.
Now,
There we go.
there's a couple of things that we have to assume. We say, number one, this is in what we call an elastic collision. The molecules undergo an elastic collision. Meaning they don't slow down.
Isn't it more the case that the collision doesn't cause an energy loss?
Correct. Because that, at the molecular level, so let's write this down. At molecular level, goodness gracious, Paul. The change in the velocity is 0 meters per second at the absolute velocity. We negate directions. Because if it started to go slowly, what does that mean? See, we have this concept when we deal with it in intro, where the molecules are moving around in this box. And people say, if it gets bigger, then move slowly. Or if you compress it, it's going to get hotter. And I'd say, well, why is it getting hotter? And they go, well, they hit each other, so there's more friction. But do you understand that getting warmer because of friction is because you have a loss of kinetic energy going into thermal energy? But at the molecular level, the thermal energy temperature is the average kinetic energy, which is 1/2 mv squared. This is not changing, 1/2. And the velocity squared must not changing. Because if it got hotter, it would move faster. But you're telling me they slowed down because they hit each other, which would make it move slower. So you can't have both. The idea is that it's an elastic collision and the molecular level.
It's
Now,
1/2 what?
mv squared. Kinetic, you know this. You know kinetic energy.
It's absolute value V, right?
Well, no, it's no. James, it's 1/2 mv squared. But because I'm squaring it, it's like taking the absolute value.
Oh, okay, okay.
This is the same kinetic energy in both, right? So, like Jim said earlier, there's no energy loss,
Energy is conserved.
right? Nothing's going on in there. Now,
So I
if I
was missing
put
something,
this
but-
molecule in this box, how much of the pressure will it account for? How does the pressure change as opposed to the force? It will only be 1/3. Can you explain why?
Pressure only changes.
Why only 1/3? Hello?
Yeah, yeah.
Hmm. Uh,
60 divided
Bruce,
by
what do you say?
I have a feeling that when you're going to differentiate something, there's going to be a 3 that's going to come out somewhere.
No, it's not in the differentiation. Here, look. The molecule is going this way. How much is going this way or up and down? Nothing. So I have 3 times the area, but I'm only having a molecule going this way. So that molecule is not doing the whole pressure. It's only doing 1/3 of what the whole pressure for the box in 3 dimensions is. You're only doing 1/3. So if I took another molecule that was going up and down, that would be the other 1/3. And if it went back and forth this way, that would be the last 1/3. Then I put them all together and I go, well, the pressure is related to the mass times the velocity, the change in the velocity with respect to time.
Okay, so it's in respect to all 3 dimensions, but in this case, it's only just in one
Right. So when you get
one
the
dimensional.
concept of thirds, that's where that number's coming from. You have 3 sets of walls in 3 dimensions. And the molecule's only, because if the molecule were going straight back and forth, it's only going to hit 1/3. But what if the molecule is kind of going around the box because it's hitting the different areas? Do you understand it's only going to hit a face of the box 1/3 of the time approximately? Now, on these worksheets here, I have the kinetic theory worksheet. So let's go ahead and open that. I'm going to view it in the show in the folder. I'm going to allow myself to open it. And then I'm going to put it into there.
do you want to open this file? Security warning, unknown publisher. I think I'll be fine.
Where'd it go?
Can this not open it?
I must have put it someplace else. Where did I move it to? Oh, here, it's here still, kinetic theory. I need to move it into that. There we go. There's kinetic theory. So now let's take a look at what we say in this. Kinetic theory, or the kinetic theory of gases. And just some stuff in here where we can do it. So let's look at the postulates. The gas consists of very small particles, each of which has a mass or a weight in SI units, kilogram. The number of molecules is large, such that statistical treatment can be applied. Molecules in constant random motion. Now, when two molecules bump into each other, what happens?
They bounce off each other?
At the same velocity?
No.
At the other's velocity.
If a molecule hits like this, and they hit over here, right? They could go at different, you could change the speed of a single molecule, but the total momentum doesn't change. So the momentum of a single molecule does not have to be equal to 0. But the momentum change of the average is 0. So we're looking at average molecules. So the thing that we look at is, what is it called? What are those little things, that balls that hit and move?
Pendulum?
No.
Newton balls?
Newton's balls or something like
Newton's
that?
cradle? Newton's cradle, I think that's it.
Newton's cradle? I think that's what it is. So let's do this. I've never looked at this, but since I'm here on a computer, Newton's cradle, and we'll look at some videos of that.
I'm asking you to make a donation right now before the official FEC deadline. And if you do,
Now, this last one is cool, right? Because what's happening is the first one, when it was just one ball, it would knock the one ball, the other three were supposed to sit there. So the momentum of the first ball created the momentum to the last ball to move equally. Okay? But when I had 3 balls hitting, I have 3 times the mass. That's going to make the 2 balls go further. They'll go faster because those 3 balls came to rest. The other 2 will go faster to make up for the loss of mass. So a molecule, if they have different masses, can change their momentum. If they have different velocities, and depending on how they hit, one molecule may go slower, the other molecule is going to speed up. So what happens is the total momentum is 0. The total momentum change is 0, but each individual may change. So molecules can move around fast, they get slowed down depending on when they hit. So that's why when we talk about temperature, it's the average kinetic energy of the molecules. Am I making sense to you guys? Say yes or no.
Yes.
Mm-hmm. Yes.
Jacob, you good?
Yep.
Okay. So we go back to the kinetic theory. The collisions of the gas particles with the walls of the container holding them are perfectly elastic. Interactions among molecules are negligible. They don't exert forces except during a collision. The total volume of the individual gases is negligible compared to the volume of the container. This is kind of interesting, just so you know. A box of air with gases flying around. If I actually looked at all the molecules, I could condense them into the corner, put them really dense, and the rest, most of the box is a volume of empty space. Molecules take up very small amount of space. Most of it is empty space. And that's what this says. The total volume of the individual gas molecules, that would be this, is very small compared to the total. This is equivalent to stating that the average distance separating the gas particles is relatively large compared to their size. So a molecule is here, a molecule is there. These are really small compared to the distance that separates them. Got it? Sorry. Molecules are negligible compared to the volume of the container. Molecules are spherical and elastic. Average kinetic energy depends only on the temperature of the system. So this is the first of the really important statements to do, is that the temperature is proportional to what? And we put a line, on top to say average. Average kinetic energy of the molecules. Which means average mass and average velocity. We say that the time dt is infinitely small. The equations of the molecules are time reversible. We could run a video camera backwards and we'd see the same thing. So here's an instantaneous, dt is 0, and elastic. It moves back. Okay. Pressure. Consider the gas of N molecules. So now we're going to use capital N as the number of molecules. Each with mass m, little m, in a cuboidal container of volume V. Okay, then I talk about acting perpendicular to the coordinate system. So watch this. And here you're going to see in calculus or in math, in science, you're going to see P standing for momentum. So this is going to be 2 times the mass times the volume. Now, why does this make sense? I mean, not the volume, the velocity. Remember we said it's moving there at 30 and then it's moving this way at 30? And so the difference in the velocity is twice the velocity. And we're going to... What?
Sorry. This is for when when the momentum is lost and gained by the wall.
This is when It's not lost and gained by the wall. It's the molecule having an elastic collision. Remember, you
Okay.
said 30, and then I went this way at 30. What's the change in the velocity? Was 60, right? But the change in the velocity is really 2 times the velocity. Because it's going positive, negative. It's the difference. And that's where this comes in here, right? 2, so 2 times the velocity in the x direction times its mass, which is constant.
Gotcha.
So the change in the momentum is 2 times the initial velocity times its mass.
So from negative 30, it goes all the way up to 30, which is technically double.
Right.
Gotcha.
Now over here, they're going to talk about in terms of how often does it impact the wall. Well, L is the length of the container. So I want you to imagine that we have a container, cuboidal container. I don't know, I keep getting larger. I must be doing something wrong, but whatever. And we're saying that the length of the container, this distance here, is length L. So the change in time between what? Between impacts. How often does the molecule go back and forth? See, this is where being older matters, because I know the video game Pong, where you see the little guy going back and forth. That's what we're looking at. So if you don't know what Pong is, you need to Google that.
So this is like the formula for Pong?
For Pong. Perfect. Okay, so the time is twice the distance divided by the velocity. Think of the velocity down here as being meters per second. And the length is a meter. And so the meters cancel, and the second goes up on top. So that is a time interval. Do you agree that if the length were greater, it would hit more infrequently?
Yes.
Yep.
Although the particle impacts the sidewall every once, L over Vx times, only the momentum change on one wall is considered. So the particle produces a momentum change on a particular wall every twice that amount of time. So I'm only looking at this wall's momentum change. And how often does it affect this wall? Every other, twice the time, twice the length. That's when there's a momentum change on this wall. Do you agree that there's a momentum change on this wall every 2 times?
Yes.
So the force, and we know this is true, the force is defined as the change in the momentum over time, which we are saying is the change in P over time. But we're not doing derivatives. We're actually saying it's easier if we talk about the total change over the time. But the total change in the momentum is 2 times the mass times the velocity in the x direction. And the time it takes and how often we do that is 2 times the length times or over Vx. So do you understand that the 2's go away and we get the mass times the velocity squared all over the length?
So it's 2mvx over 2lvx?
Yeah, I need to put an x in there.
1040.
I need to move the.
Thank you, Nick.
Yep.
So now we're saying, well, what's the total force acting on the wall? What does this indication mean? What is that thing saying?
Summation.
I'm summing up all the molecules that are doing this. Because how many molecules are hitting that wall? A lot.
A lot.
I'm looking at just the wall. Just this wall. Not both walls, just one wall. Because I want to know the force. Remember, pressure is force over area. So once I know this wall, what do you think I'm going to have to multiply by?
3.
No.
Oh, 2. Oh,
No.
wait a minute. We're just in 2 dimensions or 3?
No, I'm in 3 dimensions.
Okay.
I have this is all about, this is all taking place in a cube. But I'm only looking at the force on wall, so how many will I have to multiply by? 6,
Oh, 6 sides.
right? Now look at this. This is scary, but it's not. If it was 2 dimensions, and the molecule are moving this way, do you understand that I could break that up into this? Oh gosh. Why does it keep getting larger? What am I doing? It goes this plus this, a squared, this, oh, I'm sorry. This is this side squared plus this side squared equals c squared.
Pythagorean.
Pythagorean's theorem. If I did it in 3 dimensions, I get another triangle with a 3rd dimension. So the velocity squared is the square of the different, in this case, you could think zonal, meridional, and vertical component of the velocity of the molecule. So the molecule, in actuality, is sitting there moving around in 3 dimensions. It's bouncing all up and down on the different walls, and it's just moving 3 dimensions. So the total velocity is the x component plus the y component plus the z component, but you have to square it.
So it is just very much like the zonal components.
So the total force, we already said the force was the mass over the length in this direction. So they're doing the mass over the length in the summing of the velocities. But the summing of the velocities is really nothing more than the summing of the actual velocity of each molecule. Here they're using J to indicate J number of molecules.
So that, okay, so what you have circled is the velocity x, y, j, if you're using.
No, it's x. No, over here, this thing is the x component.
Yeah, but I'm saying on the far right.
Yeah, I'm saying
That's
that
x, y.
what we're doing is we're taking the x, the y, and the z component squared,
Right.
which is nothing more than the actual component.
Yeah, okay,
Remember that this j is representing the number of molecules.
okay. Yeah, I'm just saying what you have circled on the right, that v is in 3 space.
Exactly. So j, I guess j, is the number of molecules that they're summing up. So the total force is this, which we said, right? And we have the length, and we have 2 times the length, but then we have 1/6 because we'd have to multiply by 6 to get the total pressure, the total force on all 6 walls.
6 sides.
So you're only getting 1/6 of that. Well, guess what it becomes? 1/3,
Third.
which is the way that we talk about the molecule going back and forth. And that's a good place to start. This is where we will continue up on our stop sharing. Let me erase everything. And this is where we will end today. So for Thursday, you have to finish and turn in the worksheet, and you need to watch that little video on the mechanical universe. Now, just so you know, you are going to be reading into chapter 3, and you can read into there if you want, but you don't have to at this point. I think getting through the first 5 pages of chapter 3, the first 4 pages actually, 4.5, is difficult without having this kinetic theory down. Because they make a lot of assumptions. You're like, what? Where'd this come from? So you've got to think about why it's happening. But we'll put those two together, and that's what we're going to do on Thursday. Any questions?
No, I think that one went pretty well.
Well, that makes me happy. Because this is my least favorite section of the book. Right? This just a little bit. Once we start using it in the first law of thermodynamics, then I'm like rock and roll is my favorite.
It kind of connected a lot of the dots from the other sessions for me, so I think I've actually sort of got a handle on this now.
Okay, well then I will see you guys on Thursday, or I'll see you at forecasting class. Have a good one. Bye, guys.
Take care.
See you Thursday. Bye.